All right, ladies and gentlemen, this is going to be our equilibrium lecture 6.3a. This is when we start taking our knowledge of writing these equilibrium equations or expressions and actually start calculating with them. You'll be given information either with this kind of stuff, you give it to you in like a list or a table value. It could be in a graph, whatever it is, and that aligns with our learning objective here is that you've got to be able to calculate this equilibrium constant K. This is what we're going to have you doing here. All right, guys, so really there's two ways that we are going to be able to calculate the equilibrium constant. We can write our equilibrium expressions, and then if we know all of the equilibrium concentrations, and that's a key word there, all. So we know all the equilibrium concentrations, we just plug into the equilibrium expression and solve it out. By far, this one is the easiest. And drag that out. It's the easiest because all we have to do is simply just write the expression, plug everything in, and type it in the calculator correctly, and we're going to be all right. The second one gets a little bit more complicated, where we know some of the concentrations, but not all of them, whether we know initials or finals or whatever it is, and we have to actually do some math and some logical reasoning. Deduction to get to the numbers we need to plug into the equilibrium expression. So we'll take a look at the first one first, since it's the easiest. We'll start there. So we're going to look at our example here. We've got our equation, and this is one that we've been looking at the past couple of lectures. We know at 445 degrees Celsius, the equilibrium concentrations are the following. So we know our equilibrium concentrations. We should have 1, 2, 3 of them. We do. Check. We've got all the equilibrium concentrations. All right. So all we have to do, we're going to write our expression. I'm going to go ahead and pause it. You pause it too. Write the expression on your paper and then see if you got it correct. All right. So there's my equilibrium expression. Down here, I've got my HI squared divided by the concentration of hydrogen and iodine multiplied together. And again, this is Kc. Yeah, I could technically write Kp, but notice my concentrations they're giving me concentrations that's based on molarity. So that tells me I've got to use Kc for this reaction, even though I could technically write a Kp. All right, and so now what we do is we take these concentrations and we just plug them in. So I would literally end up with 0.11 and 0.11. All right, my hydrogen is 0.11, I plug it in, my iodine 0.11, plug it in, and then I take my hydrogen iodide and I'm going to plug that in. It's going to be 0.78 squared. All right, and I'm going to find a calculator, I'm going to type all this stuff in, plug it in, and then we are just hit enter and you get your answer. All right, so I went in and typed this in and I ended up with an answer of 50. And for this, we're going to leave the units of K is something we'll address here. My units of K, whether it be Kc or Kp, I'm going to leave them unitless. I'm not going to carry the units to over it. And generally speaking, the equilibrium constant value is going to be a unitless number. So I'm not going to have any units there at all. So my final answer is just 50. And again, this is the easiest one. If I know all the equilibrium concentrations, I just plug it into the equilibrium expression and just roll on and go. Okay? All right. Now let's take a look at the equilibrium constant a little bit more. For any reaction, the equilibrium concentrations are dependent on initial concentrations. So what that means is if I start with more, I'm going to end with more. If I start with less, I'm going to end with less. That kind of relationship. And so if we change the initial concentrations here, right? If we change initial concentrations, the equilibrium concentrations will change. All right? It's important to understand that. The equilibrium concentrations will change, but, and this is huge right here, guys. This is a big old but right here. But at a given temperature, so at a given temperature, K is always the same. So it doesn't matter what I'm starting with, that ratio of equilibrium concentrations will always be the same at a given temperature. All right? And so what I'm trying to tell you here is that if you change the temp, right, the K value changes. But if you don't change the temperature and we just change concentrations, my K value will be the same even though my equilibrium concentrations are different. And I'm going to show you a table here on this next slide and prove this to you, okay? So here we go. We've got a bunch of initial concentrations over here. And again, this is the same reaction we've been looking at. Again, it's at 445 degrees Celsius. And notice, here's my first example. This is the one that we just did, right? I take my initial concentrations, which is 0.5, 0.5. I have all of my equilibrium concentrations. I plug them in, and I get an answer of 50. All right? Now notice in the second example, if we highlight the second example and take a look at that, notice my equilibrium concentrations, or I'm sorry, my initial concentrations have changed, right? I've changed them, and then what we see is that my equilibrium concentrations are different than what they were previously, all right? But when I plug them into the equilibrium constant, this is the big part, my equilibrium constant is the same. Because we're still at 445 degrees Celsius, my equilibrium constant will be same, even though I've changed my initial concentrations and my equilibrium concentrations have changed, right? It's the ratio. That's what's important. It's the ratio is going to be the same. And then if you'll go ahead and pause it and look through the rest of these examples, and you'll notice I can do anything I want to the initial concentrations. It'll change my equilibrium concentrations, but my overall equilibrium constant will be the same. So again, all of them change. My equilibrium constant's the same on all of these. I would pause this and take a look through this and make sure that you understand this, that K is constant at a temperature. It will not change even if I change the initial concentrations, right? The equilibrium concentrations will change. They are dependent on your initial concentrations, all right? A couple of really key things that I keep saying and repeating over on this, guys. Make sure you get that stuff written down that's going to be important so you don't get stuck later on. All right, now we're actually going to get into equilibrium constant and calculating that when we don't know all of the equilibrium concentrations, all right? The good thing is that we all know stoichiometry, so we can just stoichiometrically figure it out. And the truth is, we actually only need one of them, right? We need one equilibrium concentration. As long as we have the initials, we'll be able to solve all of this stuff out. All right, so for example, I'm using again the same example that we've been using, and I'm going to go ahead and tell you my initial concentrations are 0.5, 0.5, and 0. I know, and this is a typo, it's not a change, actually that would be a change of plus 0.78. All right, so plus 0.78 is what my change was there, and so if I add, and I actually for this I would be adding because it's a product, right? Essentially, products add, and then these are my reactants over here. So my products would add up. My equilibrium concentration is 0.78. All right. So here's the thing. I look, this 0.78 is going to help me get these other two numbers that I'm interested in so that I can get down here and figure out my equilibrium concentrations. All right. So let's look back into the chemical equation. Notice the coefficient of 2 here, so the concentration of this should change twice as fast as either one of these. So all I'm going to do is come up here and take that 0.78 and I'm going to divide it by 2, right? And that'll give me both of these since the stoichiometry of them is the ratio is the same, all right? And so I'm going to go ahead and 0.78 divided by 2 I know is 0.39, so I'm going to have 0.39 as my change on both of these. So 0.39, and then notice with the products I added them, right, because I'm actually making this stuff. With my reactants, I'm going to be subtracting them. So what I'll do is I'll take 0.5 minus 0.39, and that will give me my 0.11 and my 0.11. All right, so this becomes my equilibrium concentrations that I'll be able to plug back into my calculation, because again, I'm trying to calculate an equilibrium constant, so I'm still going to have my Kc equals Hi squared divided by concentration of hydrogen times concentration of iodine. And what I do is literally, let me go ahead and change the color of my pen here, I'm going to take these values and plug them right in here, and I can solve my Kc, which we know because these numbers, this is going to equal out to 50 because these are the numbers that we used in an example previously. All right, I'm just trying to point out to you, and this is real important, this table down here, this is the first time that we've seen this, and again, let me get a different color pen here, write it in purple. This is called an ice table, right? You're going to need to know what an ice table is. I've got initial, change, and equilibrium concentrations here. This is an ice table. We're going to be setting this up. This is one of the more important types of calculations that you're going to do all year long in chemistry. We're going to cover it right here when we're in equilibrium. We're going to cover it in acid-base. When we do acid-base equilibrium, we're going to cover it in solubility and solutions. When we do solubility equilibrium, and we're going to be using this ice table for a long, long, long time. So please make sure that you understand my reactants, my change would be a negative, right? And for my products, it would be a positive change, right? Because my reactants are disappearing, my products are appearing. So please understand that. All right, moving on. We're going to take a look at one more example with you here for doing this. Again, I've got my ice table set up, right? I've got my ice table set up, my initial change equilibrium. Notice I'm given two initial concentrations. I've got a different reaction I'm working with here. And then my change, I don't know. I don't have a change on either one of them, but I do have an equilibrium concentration for my A. And so what I can do is I can come over here and I can say, well, you know, I'm logical enough. I can actually figure this out and say that this is a change of minus 0.25, right? Because 1 minus 0.25 gives me my 0.75. So 1.0 minus 0.25 equals 0.75. So this is my change, right? And this is what I'm going to plug in over here, only this is going to be 2 times, right? It's going to be 2x because of my coefficient of 2 here, so the change would be times 2, right? If this one changed for 0.25, my B would change this, so all I do is I take 0.25 times 2, this is going to give me 0.5, and so erase that out, and so my change here would be 0.5, and then notice I'm going to add here, right? And so that my equilibrium concentration now is 0.50. All right, so I've got my two values that I want here. Now all I do is I can take it back because I'm still trying to calculate this equilibrium constant. So I'm going to go up here and I'm going to write Kc since these are all molarity. And we know that because of the concentration brackets. I'm going to write my equilibrium expression, which is going to be the concentration of B squared divided by the concentration of A. And then plug in my numbers. So it would be 0.5 squared divided by 0.75. Type that into the calculator and here we go. Alright, so my Kc value is equal to, I got 0.33. And again, remember it's a unitless number. So this is what we were trying to figure out. We were trying to figure out what the equilibrium constant was. This ice table again allowed me to do this. I'm looking at these changes that occur between reactants and products. They're stoichiometrically correct. Right? So I know I can look at my coefficients to get those changes sometimes. And then just remember, the majority of the time my reactants are going to be a negative change, my products are going to be a positive change here, and I'll be able to use the table to figure out my equilibrium concentrations. All right? Please make sure you go back and look. These are two pretty simple examples, the last two that I did for using the ice table. The next part of this particular section, 6.3b, we will get pretty hot and heavy into the ice method, and hopefully you guys, if you don't know it or remember it, you can look up the quadratic formula because that's going to be coming back into play here too. Okay? Write any questions that you have down. Make sure you get your practice problems done and get those checked before you move on. And we'll see you in class.